All right. Before the break, we looked at some transfer functions of some of the systems, and a couple examples of circuits. So one of the basically what we did, we used this expression for the first order transfer function, which was basically h0 plus. So we wrote the transfer function as in terms of two transfer constants and a time constant for first order system, as h1 tau s over 1 plus tau s, where h1 and h0 were the transfer constants and tau was the time constant. Now we also saw that we could write it as, in this form, if you factor it, you can write it as 1 plus h1 over h0 tau s over 1 plus tau s. Now the key question is that, so you can clearly see that there's a pole and a zero, right? So what is the pole frequency? What is the pole? The pole is at negative 1 over tau, right? The root of this thing. And the 0 is basically at negative 1 over this. So let's write those things. P, pole, is negative 1 over tau. And z is at negative 1 over that entire expression, which is basically h1 over h0 tau, which is basically negative h0 over h1, or negative h0 over h1 times negative 1 over tau, right? Which is basically like saying 0 is h0 over h1 p. So h0 and h1 give you the ratio of the pole and the 0, right? So by looking at the ratio h1 and h0, you can tell where the 0 is with respect to the pole. And this is quite useful because by evaluating this ratio, both in terms of magnitude and sign, you can decide what kind of transfer function should a system have without writing the full transfer function or the complete analysis. So all you need to know is to know these two transfer constants, and then you can tell. So in particular, you can actually make, we can even make a table here, right? You can make a little small table here. Let's make a little table. So this is basically h, I think to keep it consistent, okay, h0 over h1. The magnitude of h0 over h1 smaller than 1, and the magnitude of h0 over h1 greater than 1. And then you can look at the sign. You can say h0 over h1 positive 1 and negative. Positive, yeah, put it first. Okay, fine. Positive in your hand. And this is h0 over h1 being negative. So there are 4 combinations. They're negative, they're positive, and then they're greater than 1 or smaller than 1. So when they're negative, when they're positive, what can you say about the poles and zeros in terms of which half plane they are in? They're in the same half plane, right? You can say P and Z in the same half plane. Half plane, same thing. P and Z in the same half plane. And then, of course, if they have opposite sign, the opposite is true. P and Z, opposite half planes. Right? So that's one thing. I mean, again, and we'll see how it applies. The other thing is that we can say something about the relatives, which one happens first, right? If h0 over h1 is smaller than 1, it means that z is a lower frequency than p, right? So this means that z is at a lower frequency than p. This. So it means z lower than p. And here it means that z is happening at a higher frequency than p. So how would this affect the response of the system? There are 2 different ways to think about this. One is to look at the frequency domain response. In terms of frequency domain response, you have 4 different kinds of responses, right? You have the phase and amplitude response for each one of them, if you look at the Bode plots. So we are going to try to do 4 Bode plots with phase and amplitude. So let's see. this case, you have a 0 and a pole that are in the same half plane, let's say left half plane, and then 0 happens at a lower frequency than the pole, right? So it means that you have a 0, you have a 0 and you have a pole like this. Both are left half plane, meaning that so your amplitude response goes up like that. And how about the phase response? The phase response of a 0 gives you increasing phase, and phase response of a pole gives you a decreasing phase. So what you can expect to see from the phase response is that the phase will go up and comes down, comes positive, right? Is that correct? I think it's correct. Just double check. Yep. So this corresponds to this case. I'm trying to kind of correspond these quadrants to that. In your handouts, there's no the spacing, the placement is different. Okay. So now the second scenario is that you have the pole. So let's talk about this one. The poles and 0 are still both left half plane, but one is happening before. Now this time, the pole is happening before the 0. So how would the response look like? It would drop in amplitude, and in phase, of course, the phase of the pole hits first, so you go down and you come back up. The phase response, right? And amplitude response. The green is the phase response, red is the amplitude response. Now, how about this case? When they are in the opposite half plane, let's say you have a left half plane pole and a right half plane 0, and it's happening before. So this is the same as that, except for the fact that this is right half plane. That's a right half plane 0. So the amplitude response will remain the same, because the left half and right half plane response look the same. But the phase response is now going to be different, because the right half plane 0 has a phase response that looks like a pole. So your phase starts dropping and then drops further to negative 180. Now, if you have the opposite scenario, again, you have a pole and a right half plane 0. Next, again, the amplitude response would look like that, but the phase response, again, will start dropping this way. So you have 4 different frequency responses based on this. You can easily tell. Now, what do you mean by being able to easily tell? Because if you're caring about being left hand and right half plane, you don't even need to calculate these things, right? You need to, for example, if you're dealing with a capacitor, you short circuit it and open circuit it, and you look at the sign of H0. You see that, and that's one of the metrics. If you short circuit something, right? For example, for you to have a 0 to begin with, you have to have a capacitor when you short circuit, it produces a non-zero transfer function or transfer constant. So if you see that there is a capacitor that you short circuit and your transfer function or transfer constant is non-zero, or a capacitor that you open circuit and your transfer constant is 0, that means that there's is non-zero. It means that you have a 0. Now, if you want to see where it is, you look at its polarity with respect to H0 when it was open circuited. If you see, for example, you have a capacitor that when you open circuit and short circuit, they have the same polarity of the transfer function, then you have a left half plane 0. Example was here, right? So this was the example. We did it before. A source follower, right? If you short circuit this capacitor, the sign of the polarity of your transfer function did not change, right? When it was open circuit and short circuit, both of them you have non-inverting gain from this input to that output. And that led to a left half plane 0, right? Which was here, right? Now, in the other case, in the case of a common source here, though the situation was different. Because you remember, if you take this capacitor and if you open circuit it, this is an inverting stage, right? The gain is negative. But if you short circuit it, then it becomes this resistive divider. And it was positive. So that tells you that the 0 is in a different half plane than the pole. Since our pole is left half plane, the 0 had to be right half plane. So by inspection, you could actually tell. Now that if you understand how it works, you can tell by inspection if something is left half plane or right half plane. Where the 0, if there is a 0, and if it's left half plane or right half plane. Okay? So that's half of the discussion. So let's go back to where we were. And then the other part of this thing is that this transfer function that we had, that we wrote in that following form, right? That h of s being h0 plus h1 tau s over 1 plus tau s, you can write it in this form. You can write it as two fractions. You can write it as h0 over 1 plus tau s plus h1, or you can write it as h0 times this, h0 times that, plus h1 times tau s over 1 plus tau s, right? You agree with that, right? So that. But now, if you look at these two terms, this and that, they correspond to a certain kind of transfer function, right? What is that first one? What kind of filter is that? That's a first order low pass, right? What is the second one? That's a first order high pass, right? So h0 and h1 are just weights or strength of a low pass and a high pass and how they're combined. Now in time domain, the time domain response, we know that every transfer function corresponds to a time domain function, right? You can define as impulse response of that, or a step response. So this goes to an impulse response, and that goes to a step response. If we look at the step response, what is the step response of a low pass, first order low pass? It's an RC, decaying RC, right? It's basically, it's 1 minus e to the negative t over tau u of t, right? And the second part is basically e to the negative t over tau u of t. In other words, this, and if you look at these, what is this one? This is the low pass one. It basically says the step response is this thing, and this part of it is, you know what, actually we can do a little bit of a color coding here. This one is simply, the step response looks like that, right? So you're weighting these two, so you have a weighted sum of these two. So you have h1 times this, and h0 plus h0 times that. So that tells you stuff about even the time domain response of the system. So in other words, what you see is the sum of these two. So if you add these two, what is your overall response? So I don't know what green plus purple would be, but okay, let's pick something. So what is the initial value at time t equals 0 of this response? At time t equals 0, this part of the response is 0. So you only have this part of the response. So you start from h1. What's the infinite value at time t equals infinity? h0. So it goes from h1 to h0. So the asymptote is h0 with a time constant tau. So if you know this, then from the relative ratio of h1 and h2 as well as the relative signs, you can come up with different times of time domain response, again by inspection. So how do we know that? So for example, let's say h0, let's say you have you're in two opposite half planes, namely the polarities of h1 and h0 are different. What would it look like? What would the transfer function look like? Well, then it means that these two will have different signs, right? h0 and h1, which basically means that your response in that case will look like this, for example. Let's say You go to one of them. Let's say, well, this would be initially would be h1. Should be h superscript 1, superscript 0. H superscript 1, you go here, and then you eventually go to, let's say, h1, h0, asymptotically. When would this happen? They have to have opposite polarities, right? To have opposite polarity means what? Means that you have, let's say if you have a left half, if it's a stable system, you have a left half plane 0, you will have a right half plane pole. I'm sorry, left half plane, if you have a left half plane pole, you will have a right half plane 0. Right? So this is called an undershoot. Right? An undershoot is the signature, the time signature of a right half plane 0 for this reason. You can easily see it. If your step response has an undershoot, so it's trying to go there, but it first goes in the opposite direction, it's because that 0 with the opposite polarity is kicking in and it's changing it. So this is the signature of a right half plane 0 in a stable system. Because the only way this can happen is that h1 and h0 will have to have opposite signs, right? And when they have opposite signs, it means that you have a right half plane 0 in a stable system because the pole has to be left half plane. Now, what happens if h0 over h1, the parameter that we are concerned about, so let's say h0 over h1 is between 0 and 1. So it means that they are same polarity, but it means also that h1 is greater than h0, right? What would you get? What would the response look like? The time domain response, right? This is t. The step response, more accurately. Well, they would be going both in the same direction, but you start with an h1 that's higher, and then you go down to an h0 asymptotically. Right? What is that? That's an overshoot. Now, this is another thing to keep in mind and remember. You don't need a second order system for an overshoot. If you see an overshoot, this is a first order system. You can get overshoot from a first order system if you have a 0. But that 0 has to be left half plane, and it has to be happening at a lower frequency than the pole. So if you have a pole, if you have a 0 that happens before, a left half plane 0 that happens before your pole, you can get overshoot. It's kind of a funny looking overshoot right now, but even if you have a higher order system, which doesn't have, it may be a damped system from that perspective, but the 0 can do this to you. This is something to, just like something that's usually overlooked. Everyone assumes that, a lot of people assume that you need to have a second order system to have overshoot. Not true. You can get it through a 0 in a first order system. And of course, if you are in a situation where it's positive and h0 is greater than h0 over h1, so if your h0 over h1 is greater than 1, then you will have a response that would look like that, kind of like a more traditional. You go up to h1, and then you eventually asymptotically go to h2. I'm sorry, h0. Does it make sense? So you can tell a lot if you look at h1 and h0 without even having to write the full transfer function. So you can see if they have opposite polarities, you will see undershoot. So for example, in our common source example with C mu, right? That was a right half plane 0. So you can actually get that. Depending on, you can get an undershoot. You can also have overshoot like in certain scenarios for certain values of the system, for certain values of the source follower, right? You can get an overshoot, even if it's not necessarily inductive. And then here you can also get some sort of a response. So you can actually tell a lot from just the h0 over h1, both in terms of time domain as well as the frequency domain response of the system. And you can tell a lot about the zeros. So, and again, this discussion can be generalized, and we will generalize it to higher order systems, but this is like a first order, the essence of that. Any questions on that? All right.